Welcome everybody to this new lecture of our paper Electronic Communication System, and today we will continue our discussion about Foster-Seeley discriminator. And in the previous lecture we were discussing about the circuit, the operation, the advantages and disadvantages of Foster-Seeley discriminator, and today we will discuss its frequency response curve. Okay, this is a curve between the input frequency f and the output voltage. This curve is known as frequency response curve, and this is the curve, the resultant curve of the Foster-Seeley discriminator. And you see here that when the frequency, the input frequency f is equal to the centered frequency Fc, the output voltage of the discriminator will be 0. Look at here. The output, when f is equals to Fc, the output voltage of the discriminator is 0. And when the frequency f, input frequency, when the frequency f is equal to Fc plus delta f, that is greater than Fc, that is greater than Fc, the voltage, the output voltage of the discriminator is maximum. Okay, and it is shown in the output as the positive voltage. And when the input frequency is equal to Fc minus delta f, that is less than Fc, so the output voltage of the discriminator is minimum, or you can say it as negative voltage. Okay, so between these frequencies, that is between the Fc and Fc plus delta f and Fc minus delta f, this is known as the useful range, because the response of the discriminator between these 2 points is linear. That's the increment of Foster-Seeley discriminator over balanced slope detector. Okay, because there is a problem of linearity in balanced slope detector, which is overcome in Foster-Seeley discriminator. Okay, and the response curve, which is normally seen for an FM demodulator or FM detector, is shown as S curve. This is the S curve, the letter S, okay, of English alphabet. And there is a linear portion at the center of response curve. There is a linear portion here is, and towards the edges the response becomes very distorted. और जैसे ही हम इन edges की तरफ जाते हैं तो ये जो response है Foster-Seeley discriminator का, ये पूरी तरह से destroyed हो जाता है. So this is all about the frequency response curve of Foster-Seeley discriminator, and also all about the Foster-Seeley discriminator. So let us start the next topic of our syllabus, which is about the ratio detector, another frequency detector, which is which is based on the same principle. That is, first we convert the FM modulated wave into a amplitude modulated wave, and then we use the concept of or component of simple slope detector, or you can say it as envelope, sorry, not simple slope detector, it's envelope diode detector, and the other circuit which is acts as the frequency limiter. Sorry, not frequency limited, it's amplitude limiter. Okay, so first see what a ratio detector, and then we see the basic difference between the Foster-Seeley discriminator and the ratio detector. Okay, so first see what a ratio detector. So in Foster-Seeley discriminator, the change in the magnitude of the input signal will give rise to the amplitude change in the resulting output voltage. Okay, this makes prior limiting necessary. So it is possible to modify the discriminator circuit to provide limiting. A circuit is so-called ratio detector. जो amplitude limiter की जो एक आवश्यकता हमें महसूस हो रही थी, जो एक ड्रॉबैक है फोस्टर-सीले डिस्क्रिमिनेटर का, कि जो आउटपुट वोल्टेज है वो इनपुट सिग्नल में वेरिएशन से चेंज होता है. यानी अगर इनपुट सिग्नल के मैग्नीट्यूड में चेंज होगा तो कॉरस्पॉन्डिंग चेंज हमें दिखाई देता है टू द आउटपुट वोल्टेज ऑफ रेशो डिटेक्टर. ओ सॉरी, नॉट फॉर इन रेशो डिटेक्टर. ओके, नॉट इन रेशो डिटेक्टर, इट्स अबाउट फोस्टर-सीले डिस्क्रिमिनेटर. ओके, जैसे ही हम इनपुट में चेंज करते हैं वैसा ही कॉरस्पॉन्डिंग चेंज हमें आउटपुट में मिलता है, जिसको हम एक ड्रॉबैक के फॉर्म में, ये जो ड्रॉबैक हमने यहाँ पढ़ी थी, ड्रॉबैक और डिसएडवांटेज ऑफ फोस्टर-सीले डिस्क्रिमिनेटर, डज नॉट प्रोवाइड एम्पलीट्यूड लिमिटिंग. और जब एम्पलीट्यूड लिमिटिंग नहीं होगा तो जो आउटपुट होगा वो डिस्टोर्टेड आउटपुट हो जाएगी, और डिस्टोर्टेड आउटपुट होगी तो वहाँ नॉइज का जो प्रॉब्लम है वो अराइज हो जाएगा. तो ये एक ड्रॉबैक है, और बहुत बड़ा ड्रॉबैक है फोस्टर-सीले डिस्क्रिमिनेटर का. इसी के बारे में यहाँ ये बात कही गई है. व्हाट इन फोस्टर-सीले डिस्क्रिमिनेटर, चेंज इन मैग्नीट्यूड ऑफ इनपुट सिग्नल will rise to the amplitude change in the resulting output voltage, and this make prior limiting necessary. तो इसीलिए फोस्टर-सीले के आउटपुट से पहले एक लिमिटर सर्किट, एम्पलीट्यूड लिमिटर को सर्किट को यूज करना नेसेसरी हो जाता है. और चूंकि ऑलरेडी कॉस्ट बहुत ज़्यादा है फोस्टर-सीले डिस्क्रिमिनेटर के, और ऊपर से हम वहाँ एक लिमिटिंग सर्किट अगर यूज कर दे तो और ज़्यादा उसकी कॉस्ट बढ़ जाएगी, तो वहाँ ये पॉसिबल नहीं हो पाता. सो जो फंक्शन, जो सर्किट इस फंक्शन को प्रोवाइड कराता है, यानी एम्पलीट्यूड को लिमिटिंग करता है, एक कांस्टेंट आउटपुट वोल्टेज हमें देता है, दैट इज नोन एज रेशो डिटेक्टर. और ये ऐसा क्यों कर पाता है, देखिए. This detector demodulates FM signal and suppress amplitude noise without the need of amplitude limiter stage. तो इस तरह का हमारा पास होता है सर्किट डायग्राम ऑफ रेशो डिटेक्टर. अब देखिए चेंजेस क्या हैं जो फोस्टर-सीले डिस्क्रिमिनेटर. देखिए हम एक फ्रीज यहाँ स्टडी कर रहे हैं. हम स्टडी करके आए हैं सिंपल स्लोप डिटेक्टर. सिंपल स्लोप डिटेक्टर की जो ड्रॉबैक्स थी वो दूर की गई बैलेंस्ड स्लोप डिटेक्टर में. बैलेंस्ड स्लोप डिटेक्टर की जो ड्रॉबैक्स थी वो दूर की गई फोस्टर-सीले डिस्क्रिमिनेटर में. और जो फोस्टर-सीले डिस्क्रिमिनेटर में जो सबसे बड़ा ड्रॉबैक सामने आया वो ये था कि जैसे ही इनपुट सिग्नल के मैग्नीट्यूड में चेंज होता है तो कॉरस्पॉन्डिंग आउटपुट वोल्टेज चेंज हो जाता है. तो वहाँ एक एम्पलीट्यूड लिमिटर की आवश्यकता महसूस की गई, और उसको दूर करने के लिए हमने इन्वेंट किया रेशो डिटेक्टर. अब देखिए चेंजेस क्या हैं, यानी फोस्टर-सीले डिस्क्रिमिनेटर के सर्किट में और ये जो रेशो डिटेक्टर का सर्किट हम स्टडी करने जा रहे हैं, इसके सर्किट में और फोस्टर-सीले डिस्क्रिमिनेटर के सर्किट में क्या डिफरेंस है. फर्स्ट डिफरेंस इज दिस: द डायरेक्शन ऑफ डायोड D2 इज रिवर्स्ड. दैट मीन्स, look at here, this is the circuit diagram of Foster-Seeley discriminator or phase discriminator. In this discriminator, the direction of this diode and this diode, this is the diode D1, this is the diode D2, and the direction of these two diodes into the forward direction. Okay, but look at here. In the case of ratio detector, the direction or biasing, you can say it as biasing, the biasing of the diode D2 is reversed. Okay, this is the first difference between ratio detector circuit and Foster-Seeley discriminator circuit. Okay, second difference is this capacitor C, this capacitor C. Okay, this is a large value capacitor used in this circuit, which helps to maintain a constant amplitude of resultant voltage. Okay, and the third difference is the output, the points of output by which the points by which the output is taken between these 2 points, P1 and P2. So this is the third difference between the Foster-Seeley discriminator and the ratio detector. Okay, so by these three modifications, the new circuit is known as ratio detector. Okay, and there are three blocks, you can say it as. There are three blocks which functioning, different functions are there for these three blocks. So the first, this block is used to convert the FM signal into AM signal, or you can say it, this is a conversion of frequency modulated wave. By this block we can convert the frequency modulated wave into amplitude modulated wave. Okay, and this is the second part. This is the second part, and this part is used as envelope diode detector block. There are two diodes which are used to detect the modulating signal from an amplitude modulated wave, which is used as the input of these two diodes. So this block is used as envelope diode detector block. And this, the third block, this block is used as amplitude limiter. Okay, and because of this block, there is no need to an extra amplitude limiter stage. Okay, this is an inbuilt amplitude limiter in the ratio detector. So there is no need to a separate amplitude limiter stage, to employ a separate amplitude limiter stage to the output of this block, envelope diode detector block. Okay, so this is the inbuilt circuit which is work as amplitude limiter. So basically the function is that this block converts the FM signal, FM modulated wave, into amplitude modulated wave, that is frequency modulated wave, which is used as the input of this block. This block converts this FM modulated wave into amplitude modulated wave, and this wave, which has input as amplitude modulated wave, convert that amplitude modulated wave and extract from there the modulating signal, and this modulating signal is given to this block, and this block maintains the amplitude of the modulating signal, or we can get a constant modulating signal which has constant amplitude. So these are three blocks which have different functions. Okay, ऑपरेशन मैकेनिज्म के ऊपर बात कर लेते हैं. The ratio detector, here is operation and mechanism. There are three differences between the Foster-Seeley discriminator and the ratio detector. We already discussed that. The operation or working mechanism of this ratio detector. The ratio detector used to convert instantaneous frequency variations into instantaneous amplitude variation, which is the function of this block. Okay, capacitor C retains most of its charge because of long time constant offer in the combination with R1 dash and R2 dash. Look at here, this circuit, only this circuit. Okay, look at here. Only this circuit. This circuit. Okay, because here is this capacitor C, which is a large valued capacitor, and this is in the parallel of these two resistors R1 dash and R2 dash. So these two resistors into the parallel of this capacitor makes the time constant CR, because these two resistors are in series, so resultant is R1 dash plus R2 dash, and when this resultant is multiplied by this C, the large valued capacitor C, gives you the time constant of this capacitor. The time constant is known as the time taken by this capacitor to complete charge or complete discharge, or you can say it as more simply is complete discharge. The time taken by this capacitor to completely discharge. Okay, so because the value of C is taken so large, so the time constant of this capacitor will be very large. So if there is any amplitude variation into the output, between, which is taken between these 2 points P1 and P2. So if there is any variation in this output because of the large time constant of this capacitor, so the output will maintain automatically, because time constant, the time it takes to completely discharge is very high. So if there is any variation into the output, this is overcome by this capacitor C. That's why this capacitor is employed here, and this is inbuilt circuit. So there is no need to an extra amplitude limiter stage to limiting the amplitude of the ratio detector output. Okay, so let us move forward. Now the slow charging and discharging helps to maintain the output. We discussed just now about this. The ratio detector is not affected by amplitude variation on the FM wave. The output of detector adjusts itself automatically to the average amplitude of the input signal, and capacitor C charges to sum of the voltage across R1 and R2, and because of its time constant tends to filter any noise component, because this is work as a band pass filter. So this combination C and R, this combination is used as the band pass filter, so the noise component will extract there. And finally, the priority of voltage in the lower capacitor is reversed, and the voltage V01 and V02 across two capacitor is added. Okay, this is about the operation. And now talking about the mode of operation. What are the mode of operation of ratio detector? So first mode is when F is equals to FC. That is, the frequency of the incoming frequency is equal to the center frequency by which this coil of the transformer, that is the primary of the transformer, and this is because this is by this coupling, this is center tapped here. So by this coupling capacitor, the voltage V in voltage is also here. Let us some description or describe this circuit. This is the, let us make some clarification. This talking about this circuit. So this circuit. Okay, so here is V over input voltage. This is the primary of the transformer. and tuned at a frequency Fc. Okay, and because of this coupling capacitor Cc, the secondary of the transformer is also tuned to the same frequency Fc, that is the center frequency. Okay, and this is the primary of the coil. This is the capacitor which is located in primary. This is LP, inductor of primary, and this is a capacitor which is employed in the secondary. This is the capacitor CS which is employed into the secondary of the transformer, and this is the voltage VL1, because the secondary is center tapped here, so the upper half has voltage VL1 and the lower half has voltage VL2. So the voltage across the diode D1, this is V in plus VL, V in by this RFC coil, and VL1 is due to this circuit, the secondary circuit. Okay, and because there is only one capacitor, so the upper half voltage will be plus VL1 and the lower half is voltage is plus VL2, or you can say it by mutual inductance between these two coils. The upper half voltage is plus VL1 and the lower half voltage is plus minus VL2, and because this diode is in reverse bias, that's why to operate this diode, this voltage should be minus, and this will be happened by the mutual inductance between these two coils. This can be made by these coils, this phenomena of mutual inductance. By the phenomena of mutual inductance, the voltage developed to the upper half of this coil, secondary coil, is plus, and into the lower half is minus. So when VL1 is plus, this diode D1 is operate, and VL2 is, when VL2 is minus, this diode D2 is operating. Okay, now so actually here is the input voltage. Input voltage come when the frequency F is equals to, the first case, the first mode of operation we will discuss here, when the incoming frequency is equals to the centered frequency by which the primary as well as the secondary of the transformer is tuned, when the incoming frequency is equal to this frequency Fc. When this will happen, then the voltage VL1 is equal to the voltage VL2, and because these are opposite voltage, so let us see what happened here. This. So when F equal to Fc, that is the frequency of the incoming wave, which is used as an frequency modulated wave, is equal to the center frequency by which the primary and the secondary of the transformer is tuned. Then what happened here? Let us see this. When the frequency of the incoming frequency modulated wave is equal to the tuning frequency of primary as well as of secondary transformer, the voltage VD1 is and VD2 across the diode D1 and D2 respectively same, and hence the net output of the ratio discriminator or ratio detector is always be 0. That is V out is equals to 0. Kaise? Since V naught dash T, what is V naught dash T? Let us look again this figure and let us zoom it. Okay, zoom it so high you can clearly see this. V naught dash. Okay, this is the value, this is the output voltage V naught dash, because we have to take output voltage between these 2 points. That's why we called this voltage appears across the resistor R1 dash and R2 dash is known as V0 dash. And because these two resistors are in the series with each other, so the total voltage across these two resistors, that is V0 dash T, is divided equally between these two resistors. That is, the voltage across the resistor R1 dash will be V0 dash by 2, and also the voltage across the resistor R2 dash will be V0 dash by 2. Also, one thing, let us say that the voltage across the resistor R1 is V01 and the voltage across resistor R2 is V02. So actually the voltage output is taken between these 2 points, P1 and P2. So remember this thing, V0 dash is the voltage of, you can say it as the voltage of this capacitor C, or the voltage between these two resistor R1 dash and R2 dash, which are in the series combination, and because of series combination this voltage V0 dash is divided equally between these two resistors. That is, the voltage across resistor R1 dash is V0 dash by 2 and the voltage across resistor R2 dash is V0 dash by 2. Okay, so let's see. So this is the voltage V0 dash T, which is equal to V01 plus V02. Why? Because normally when we talk about the Foster-Seeley discriminator, we have to take the output voltage between these two resistors R1 and R2, and the output voltage is taken in this manner. Let us see this. So forget for some time that there is nothing on this side. There is nothing on this side. That is, my hand is overlapped this circuit, and you are only left with this circuit only. This circuit. So what is the output voltage between the resistor or across the resistor R1 and across the resistor R2? What are the output voltage between these two resistors? The output, and this will now act as a Foster-Seeley discriminator. This whole circuit is now acts as a Foster-Seeley discriminator. Expect this one thing. Except this one thing. That is, the diode D2 is reverse biased in this circuit. Except this thing, the whole circuit is behaved as a Foster-Seeley discriminator if I removed this function which is overlapped by my hand. Okay, so now this is a Foster-Seeley discriminator, and the output is taken between the across this resistor R1 and this resistor R2. ये यहाँ इन दोनों रेजिस्टर्स के बीच में जो भी मुझे आउटपुट मिलेगी, दैट इज माय रिजल्टेंट आउटपुट. ओके, और ये आउटपुट मैंने कहा है, ये आउटपुट जो पहले रजिस्टर के अक्रॉस आउटपुट है वो मैंने कहा है V01 है, और दूसरे रजिस्टर के अक्रॉस जो वोल्टेज है वो मैंने कहा है V02 है. ओके, सो इफ दिस इज Foster-Seeley discriminator, then output voltage can be written as the V out. For the case of Foster-Seeley discriminator, this can be written as V01 minus V02 because of opposite polarity of this diode. Because in Foster-Seeley discriminator, the two diodes are in the same direction. So these are in Foster-Seeley discriminator, these are in the forward bias conditions. So that's why this output voltage will be negative. But because in ratio detector this diode is into the reverse bias, so why this voltage V02 will be negative. This is the case of Foster-Seeley discriminator, FSD, and this is the case of ratio detector. Okay, so the output voltage of Foster-Seeley discriminator for time being, let us consider this. So V01 plus V02, and this plus is coming because of this diode is reverse bias here, because this diode is reverse bias here. Okay, so let us now move to this topic. So V naught dash T, this V naught dash T, which is equal to V01 plus V02, and the output is taken between these 2 points, P1 and P2. So what is the next? This is my V naught dash out. This is my V naught dash out, because the net output voltage is taken between those 2 points, P1 and P2. So net V out. So net V out is equal to this voltage which is occurred at P2. So V at P2 minus V at P1. And what is V at P1? V at P1 is V02. Okay, and V at P1 is this V0 dash by 2. This in this loop. What is the voltage at P1 is V02, and what is the voltage at P2 is V0 dash by 2. So put these value. Vp2 is V0 dash by 2 and Vp1 is V02. So put here. Vp2 is V0 dash by 2 minus Vp1 is V02. And what is the value of V0 dash? This. V0 dash is this. V01 plus V02. So put here. Let us make this substitution here. So V out is equals to V0 dash by 2. Okay. And V0 dash out is this, V01 plus V02. So V01 plus V02 by 2 minus V02. Okay, and if this is multiplied here, so subtract from here is V01 minus V02 by 2. This is the output voltage of a ratio detector, which is exactly half of Foster-Seeley discriminator output. This is the Foster-Seeley discriminator output, FSD output. This is the Foster-Seeley discriminator output. Okay, and this is the ratio detector output. And look at these two results. Actually, the ratio detector output is exactly half of that in the case of Foster-Seeley discriminator. This. Look at these two results, and look at here now. Look at here now. This result. That is V out is equals to V01 minus V02, which is exactly half the voltage we get in the case of Foster-Seeley discriminator. Okay, so that's all for now, and meet you into the next one. Thank you.